Dear students, in the last lecture we had learned that every convergent sequence is bounded. But however, every bounded sequence is not convergent. Take the real sequence minus 1 plus 1 minus 1 plus 1, that is minus 1 to the power n. Xn is minus 1 to the power n. Is it bounded? No, it is not. Yes, it is bounded. Sorry, it's bounded. It's bounded by the number 1 because modulus of any quantity minus 1 or plus 1 is 1, so it is bounded by the number 1. K is 1, say. But it does not tell us, that the sequence is convergent, because here the sequence doesn't move towards any value, but it just oscillates between the two numbers minus 1 and plus 1. So if I just have a bounded sequence, if I cannot talk about its convergence, what can I say about it? This is where the notion of subsequence becomes tremendously important. For real sequences, it was first proved independently by Bolzano and Weierstrass. Weierstrass, while a famous German mathematician, Bolzano, a priest. Possibly he was a priest in Prague, in the Czech Republic, the capital of the Czech Republic. Bolzano is famous for giving the intermediate value theorem about continuous functions. Those who have known about it, please, for real analysis, would remember Bolzano's name. So, Bolzano and Weierstrass proved this very important fact for real line, that every real sequence which is bounded must have a convergent subsequence. That is, that you can find at least one subsequence which will go towards the limit. For example, if you take the limit minus 1 plus 1, sequence minus 1 plus 1 minus 1 plus 1, I choose just subsequence only 1 1 1 1 1 1 1 1 1. The second one, the first, the fourth one, the sixth one, the eighth one, and so on. Those indices of the sequence. So that sequence 1 1 1 1 1 is converging to. This is a subsequence which converges to 1, or I can choose minus 1 minus 1 minus 1 minus 1. So that is also converging to minus 1. So there are two subsequences, and both are convergent to two different values, 1 to plus 1, 1 to minus 1. If you have a bounded sequence actually, and if you find subsequences, that all subsequences which are convergent converges to a fixed number, then actually the sequence is convergent. So how do I know whether a bounded sequence is convergent? So I know that there are subsequences which converge. So for all such subsequences which converge in that sequence, if I can show that all that subsequences converges to a single number, then the sequence itself is convergent. So that is the way we can test the convergence, whether the bounded sequence has a convergence property. So this result, that every bounded sequence has a convergent sequence, is already taught to you in the calculus classes. I have no idea whether you have given any importance to learning the proof, because learning proofs is a very important aspect of understanding mathematics, whether you are understanding it for your pure purpose of joy, or you are understanding it because you want to apply it somewhere. Knowing to do a proof is important, because even if you do economics is filled with doing a lot of proofs, and then it is the same logic, same mathematics that you have to do those proofs. So learning to do proofs is a very important tool an economist should have in his bag. Now here you might say, if you read the whole thing, or you might have read the notes, that you are playing a trick with us. So what is that trick? You are telling that, okay, look here guys, that I know about the Bolzano-Weierstrass theorem for a real line, that if you have a sequence of real numbers which is bounded, then it must have a subsequence which is convergent. Once I take this, then I can actually apply it on a higher dimensional sequence. You are right, possibly I am doing a little cheating here, but this is a result which you are supposed to know. But I assume that most of you have forgotten the proof, so I will give you a supplementary note proving this for the real line. But for this moment, you assume that we know this thing for the real line. Okay. But if you want, you can look up the net, you can just Google it and you can find it, because Google is the biggest library in the world now. So here the proof that we take here is taken from the book which I have been very fond of, the companion to analysis by T.W. Corner. In this book, what we learn is the following. You consider a bounded sequence in R2. From this book, we learn the following way to prove it. So, consider a bounded sequence in R2. Okay. So, every sequence xn is actually a coordinate. So, each sequence xn can be written as a coordinate yn zn. Now, norm of xn is less than equal to k. So, norm of xn is nothing but mod yn square plus mod zn square, and that is less than k, which simply shows that mod yn is less than equal to k and mod zn is less than equal to k. Here you can put k less than equal, greater than equal to 0 also if I assume that all the xn is 0. But if all the xn is 0, then it doesn't mean anything. So, okay, this is fine. So, I am assuming that these real sequences yn and xn, I already know about the Bolzano-Weierstrass theorem, and I am just pushing it up into the higher dimension. This is a much easier task than actually proving the Bolzano-Weierstrass theorem on the real line, where I had to use this. I wanted to use something called the nested interval theorem. Nested interval theorem says that if I start with the interval a1 b1 and then my interval a2 b2 lies within a1 b1, then a3 b3 lies within a2 b2. So the length of the sequences are going towards 0. Then all these sequences, if they are non-empty, then their intersection is non-empty. So that is called the nested intersection theorem, and that's what is used to prove the existence of the limit point of a convergent subsequence. Now here, as I told you, I am assuming that yn and zn are two bounded real sequences on which Bolzano-Weierstrass theorem, which I know for real numbers, which is actually the real on which Bolzano and Weierstrass did, is applicable. Now, hence for the sequence yn, there is a sequence ynk which converges to y star. Now, consider the subsequence znk. So, I have ynk which converges to y star. I know there is a subsequence. Now, what I do, I will take the zn sequence, and from that, corresponding to the same indexes of that of yn, which the same indexes of ynk, the k indexes that has given me a convergent sequences in yn, I will choose the same corresponding indexes in the sequence zn and form a new subsequence znk. But that subsequence is also bounded. And again, by applying Bolzano-Weierstrass theorem, we will get a subsequence znkz, which will converge to z star. Now, what I will do, I will choose ynkz, that is the same z corresponding to that z, the z sequence, the ynkz within as a subsequence from the subsequence ynk. But since ynk is converging to y star, ynkz will also converge to y star. So, we will form this new vector xnkj, and I leave it to the reader, but I have already told you, because what happens, ynk is a subsequence from yn and it converges to y star. Now, if I take any subsequence from ynk, it will also converge to y star, which we know that if a sequence is convergent, then any subsequence of it converges to the same limit. I gave you as an exercise, and I think you should try and do it. Then, what happens is that so what happens, we construct this sequence xn kz. So what I did, I first took a yn sequence, and from there I got a subsequent ynk which converges to y star. Then I took the sequence zn, and from there I found a subsequence which is corresponding to the same case of those ynks, and I formed the new subsequence. And from that, but this new subsequence is also bounded, and hence again applying the Bolzano-Weierstrass theorem on it. Because you might say, okay, why didn't you just, maybe that znk that you have constructed would converge? It may, but I do not know whether that is a convergent subsequence. But I know that it is a bounded sequence, and hence on it I will apply the Bolzano-Weierstrass theorem to get a new subsequence znkz of znk, which will converge to some z star. Now y and k is converging to y star, so if y and k z, which corresponding to the same z of z and kz, will also converge to y star. By applying the fact that if a sequence converges, all subsequences will converge to the same limit. And hence, x and kz, if I form as y and kz and z and kz, then x and kz will go to x star, where x star is nothing but y star and z star, which shows that x star, though x and kz is the subsequence that we have constructed which has a limit x star. And that ends the Bolzano-Weierstrass theorem. So, I end the talk here, and a supplementary note will come on Bolzano-Weierstrass theorem on a single line. See, this result has to be known because as we gradually move up, we will show how things become involved. Okay, that will be how we'll see how Bolzano theorem, Weierstrass theorem becomes important. Okay, thank you very much.